molecular structure. If you recall, we said molecules are two or more atoms that are linked together by a covalent bond. They're sharing electrons. And so the tendency of atoms to share electrons depends on their valence configuration. Okay, the valence configuration refers to the outermost configuration of the atom. So for example, carbon here, it has an electron configuration of 1s2, 2s2, 2p2. What that means is that it has 4 electrons on its outermost shell. Okay, and one thing atoms in a group in your periodic table have in common is that they have the same number of valence electrons. So they all behave the same way. So when we talk about chemical properties of atoms, we're talking about their tendency to lose, gain, or share electrons. That primarily depends on how many electrons they have on the outside of on their outermost shell, their valence electrons. Okay. So for example, here in this question, which is the same number of valence electrons as the carbon atom. Here's carbon. Okay. And would it be nitrogen or silicon? Okay. So carbon and silicon are in the same column of your periodic table. They have the same number of valence electrons. They both have 4 valence electrons. That's why they call this group is called group 4A. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. Fluorine has 7 valence electrons. And if you remember, we said the atoms that are primarily involved in covalent bondings are the ones on the right-hand side of your periodic table, the nonmetals. Okay? So sulfur then would have how many valence electrons? It's right below oxygen, so we expect sulfur. It belongs to group 6A, so we expect sulfur to have 6 valence electrons. Okay? So the octet duet rule says, okay, this is a pattern that's been observed, that atoms tend to acquire a noble gas-like configuration. That means they tend to have 8 valence electrons, just like the noble gases, okay, or 2 valence electrons like helium. So hydrogen has if hydrogen were to gain an electron, it tends to gain just 1 electron to become noble gas-like, because helium has 2 electrons. Okay, so that's why this is known as the octet duet rule. Nitrogen, we say, will have a tendency to gain 3 electrons. Okay, to become isoelectronic with neon. Now, when it's sharing electrons, it also tends to follow that pattern. So that's this octet duet rule is a little bit more, is somewhat general. Okay. So, what would be the electron configuration of magnesium ion? Well, magnesium ion is right here. Okay. And so, magnesium ion would be, well, magnesium. Electron configuration of magnesium would be 1s2, 2s2, 2p6, 3s2. It will have 2 valence electrons in its outermost shell. If it loses those 2 electrons, it ends up having 10 electrons. So this is what you would call your neon core for magnesium. Neon core 3s2. So it would be, we say it's isoelectronic with neon. Okay, so we're going to say magnesium plus 2 has the same electron configuration as neon. Okay. Hydride ion tends to be has to acquire a helium-like configuration. So we say hydride would be H minus, and so its electron configuration would be 1s2. Hydrogen by itself has just 1 electron in the 1s. A second electron would give it a helium-like configuration. Right? Now, a Lewis dot symbol is a symbol that shows the valence electrons as dots around the symbol for an atom. So, for example, carbon. Okay, how many electrons did we say carbon has? Valence electrons. It belongs to group 4A, so it has 4 valence electrons. So the Lewis dot symbol for carbon would have 4 dots. So you draw you write the letter C and then draw 4 dots around it. 1, 2, 3, 4. That would be what you would call the Lewis dot symbol. Okay. Now, The Lewis dot symbol for a monatomic ion will show the valence electrons as dots around the symbol for the atom. Okay, but when we do that, we have to enclose the symbol in square brackets to indicate the charge on the upper right hand side as a superscript. So for example, magnesium plus 2, okay? What would be the Lewis dot symbol for magnesium plus 2? You would say, all right, magnesium is in 2A, group 2A, so it's going to have 2 valence electrons. So magnesium atom is going to have 2 dots. You can write those 2 dots that way. It doesn't really matter how you write it. You can write it that way as long as you show 2 dots. But magnesium ion, magnesium with a plus 2 charge, would not have those 2 dots anymore because the 2 plus means 2 electrons lost. But then to draw the Lewis dot symbol for this, you say it will have no dots, but you'll have to enclose it in brackets and indicate the charge on the upper right hand corner. Okay? Now, what about fluoride? Let's talk about fluoride. Fluorine belongs to group 7A. Okay, so it's going to have 7 valence electrons. So fluorine is going to be drawn with 7 dots. The way you do it is you can just go around 1, 2, 3, 4, and then pair up 5, 6, 7. Okay, so 2. Okay, so you have 2, 4, 6, and then that's a 7th electron. This is the Lewis dot symbol for fluorine. It's got 7 dots. 1, 2, 3, 4, 5, 6, 7. Now, if you're talking about fluoride ion, then you're talking about a fluorine atom that has gained 1 electron. So F minus has 1 extra electron. So that means instead of 7 dots, you're going to have to draw 8 dots. 7 plus 1 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. But if you do that, it now has a negative charge. Make sure you enclose it in square brackets and put a negative sign on the outside. Okay? All right. So here's a clicker question. How many electrons are shown in the Lewis symbol for a nitrogen atom? Here's your nitrogen atom. Would it be 5, 7, 8, or 14? Okay, very good. 5 valence electrons because it belongs to group 5A. Okay, that's the way you use periodic table to figure this out. Okay, how many dots are shown in the Lewis symbol for a nitride ion? Okay, this is not nitrogen atom, it's an ion. So is it going? So here's nitrogen. Okay, and we said that the tendency is for them to become isoelectronic with a noble gas. So how many dots are shown in the would be shown in the Lewis symbol for a nitride ion? 5, 7, 8, or 14? See, very good. 8. Okay, nitride ion is N with a negative 3 charge. The nearest noble gas there would be neon, so it tends to become isoelectronic with neon. 8 valence electrons, and that's an illustration of what we call the octet rule. Okay. Now, Lewis structures are what we use to represent molecules in the simplest possible way. And what we do is we show in a Lewis structure how the valence electrons are distributed among the atoms in a molecule or a polyatomic ion. It also shows how the atoms are connected. Okay? When we draw Lewis structures, we represent valence electrons by dots, or you may use a dash to represent a pair of dots. Okay? And then electrons that are shared by 2 atoms are drawn between symbols of atoms. So if I have symbol of carbon and a nitrogen and I draw a line between them, that's a pair of electrons that's shared between them. Okay? And if you have a Lewis structure for a polyatomic ion, make sure you enclose it in brackets and you indicate the charge on the upper right-hand corner as a superscript. Okay, so let's take a look at an example. Here's the Lewis structure for a molecule called urea. Okay. Let's look at this Lewis structure right here. How many valence electrons are shared here? You have, okay, those are the ones that are drawn between symbols. So that's a pair. So that's 2, 4, 6, 8, 10, 12, 14, 16. So 16 are shared. Okay. And how many are not shared? Those are the dots that are shown that are not shown between symbols. So here's a pair of dots. So that's 2, that's 4, that's 6, and that's 8. So this structure shows 24 valence electrons total. Should there be 24 though? That's one way to check if a Lewis structure is correct or not. Is, you know, what the first thing you need to check if you want to verify if a Lewis structure is valid or not. Then you say, okay, how many hydrogens do we have here? 1, 2, 3, 4 hydrogens. How many valence electrons can you get from a hydrogen? Each hydrogen atom will contribute 1 valence electron. So there's 4 of them. That gives you 4 valence electrons coming from the hydrogen. Then you look at the nitrogen. You've got 1, 2 nitrogens. All right. Each nitrogen, okay, a nitrogen atom belongs to group 5A. So each nitrogen has 5 valence electrons. There's 2 of those. So 5 times 2 will give you 10. Contribution from nitrogen would be 10 valence electrons. What would be the contribution from carbon? You have 1 carbon atom right here. So carbon atom contributes 4. And there's 1 carbon atom, so 4 times 1 is 4. And then finally, you have 1 oxygen atom over here. An oxygen atom belongs to group 6A. Okay, so it's going to contribute 6 valence electrons. So your oxygen will give you 6 valence electrons. There's 1 oxygen atom, so that's 6 times 1. So that's 10 plus 10 plus 4, 24 valence electrons. So this structure is correct as far as number of valence electrons is concerned. Okay, so that's how you would interpret a Lewis structure. A line between symbols or dots between symbols are shared electrons. Dots that are not drawn between symbols are lone pairs, unshared electrons, unshared valence electrons. Some terminologies. If you have 1 shared pair between 2 atoms, we call that a single bond. So that's a single bond right there. And that's a single bond, that's a single bond, that's a single bond, that's a single bond, and that's a single bond. So here you have 1, 2, 3, 4, 5, 6 single bonds. Okay? And you have 2 lines or 2 pairs of electrons between atoms. Then you have a double bond or a double covalent bond. So this one right here is a double bond between the carbon and the oxygen. If you have 3 pairs, you have a triple bond. In this structure, you don't have a triple bond. And then if you have an unshared pair of electrons, those are called lone pairs. So we say the oxygen here has 2 lone pairs. Each nitrogen has 1 lone pair. Okay. Now, Lewis structures for polyatomic ions should account for the charge. So for example, if I were to ask you to draw the Lewis structure for sulfate, how many electrons would you need to show? Then you're going to say, okay, sulfur belongs to group 6A, so that should give me 6 electrons. Okay, 6 valence electrons. Oxygen also belongs to group 6A, so each oxygen should also give me 6 valence electrons, but I have a subscript of 4 here, so times 4. That would give me a total of 24 valence electrons coming from the oxygen. So all in all, for the 1 sulfur and 4 oxygens, you have 24 plus 6, you would say 30 valence electrons. But, okay, you have a negative 2 charge here. So the negative 2 charge means 2 additional electrons. So 30 plus an additional 2, that would give you a total of 32 valence electrons that you have to show if you are to draw the Lewis structure for sulfate. Okay? And then once you've drawn that, you have to put it in square brackets and you put the charge on the outside with the negative 2. Now, what about ammonium ion? How many valence electrons would you need to show? Nitrogen, group 5A. So 5 electrons from nitrogen. Hydrogen, there's 4 of them. Each hydrogen has 1 valence electron, so 1 times 4 gives you 4. That's a total of 9. Okay, but ammonium has a plus 1 charge, so a plus 1 means 1 less electron, right? So that means you subtract 1, you only need to show 8 valence electrons for the Lewis structure for ammonium ion. All right. Now, in stable molecules and polyatomic ions, the atoms tend to follow the octet or duet rule. Notice I said tend to follow. They don't have to follow the octet or duet rule. But if you have to make an intelligent, reasonable guess as to how they're sharing their electrons, your best bet would be the octet duet rule. Okay? How is this illustrated in the structure below? Let's take a look at the nitrogen atom. Look at the nitrogen atom here. This nitrogen atom, okay, is surrounded by 2, 4, 6, 8 valence electrons. Remember, a line is a pair, right? A pair of dots is 2 electrons, so you have 8 electrons. So that nitrogen is, we say, is surrounded by an octet. How about this carbon right here? It's also surrounded by an octet because here you have 2, 4, and then plus 2 pairs there. That's another 4, okay? 4, 2, and 2. You have an octet around carbon. All right, so carbon in this structure follows the octet rule. The oxygen in this structure also follows the octet rule. There's a lone pair, that's 2 electrons. There's another lone pair, that's 2 electrons. That double bond, that's 4 electrons. So 2 plus 2 plus 4. We say oxygen is surrounded by 8 electrons in this structure. In other words, the general pattern that you'll find is when atoms share electrons, they tend to do so that each one gets a noble gas-like configuration around it. So that's why the noble gases are called the noble gases. You can think of atoms as aspiring for nobility. Okay? And the way they acquire nobility is by acquiring a noble gas-like configuration. Hydrogen does it by just doing one bond. So hydrogen, the only way hydrogen bonds with other atoms is shares electrons with another atom is by having a single bond. Okay, so hydrogen has to be what you would call a terminal atom. You cannot put hydrogen in between 2 atoms because that would give it 4 valence electrons around it. Okay, so hydrogen can only form a single bond. Okay, so hydrogen follows what we call the duet rule. It gets a duet, whereas all the other atoms tend to acquire an octet. Now, there are exceptions, okay, and we're going to talk about that later, but the general pattern is when atoms form molecules or polyatomic ions, when they share electrons, they tend to do so in a manner that gives each atom a noble gas configuration around it. All right, so how do we draw Lewis structure? Here's a strategy you can use to draw Lewis structure. If I gave you a molecule and asked you to draw the Lewis structure, first thing you need to do is just connect the atoms with a single bond. Okay, all the atoms, link them up. And then add lone pairs to complete the octet around each atom. Of course, if you have hydrogen, you only need a single bond to the hydrogen. You don't need lone pairs for hydrogen. Okay, you only need an octet. And then what you do then is you count available electrons to check for consistency. You want to make sure that you're just showing the right number of valence electrons. Okay, and if you don't have enough, then you have to remove lone pairs from neighboring atoms and replace it by a bonding pair between them. Let me illustrate that with carbon monoxide. Okay, so let's say I wanted to draw the Lewis structure for carbon monoxide. So I'm going to link up carbon and oxygen with a single bond. Okay, so that's step one. And then the next step is I'm going to complete the octet around each atom. So carbon has 2, okay, 2, 4, 6, 8 to get an octet. So I need to put 3 lone pairs on carbon in order to have an octet around it. For oxygen, to get an octet around oxygen, I need 3 lone pairs as well. Okay, so this will now give me 2, 4, 6, 8. I have an octet around the oxygen. Once I've done that, I check, well, how many valence electrons am I showing here? A quick way to count is to say, here's 6, and here's 6, and that's 2, right? 6 plus 2, that's a total of 14 valence electrons. Well, next thing I do is I ask myself, how many electrons should I be showing for carbon monoxide? You go back to your periodic table, you say, okay, carbon should give me 4, group 4, and an oxygen should give me 6. So 4 plus 6 should give me a total of 10. That means the structure I'm drawing is not correct because it's got 14. Okay, I only need 10 valence. I only have 10 valence electrons to distribute. So if you don't have enough, what you do is you do more sharing. Okay, so what I'll do is I'll remove a lone pair from here, and I'll remove another lone pair from here, and then replace that by another bond between another shared pair between the two. So I'm replacing 4 by 2. So I'm subtracting 4, I'm adding 2, right? So instead of 14, I now have 12 valence electrons. So that's still not right. So how do I get down to 10? I take another pair of lone pairs. So I'll take this one and this one. I take out 4 and I add another pair in between the carbon and the oxygen. Now I subtract 4 again and I add 2. I now have 10 valence electrons. So let me clean up that structure. Okay. Check out these. Take these out. And what do I have here? I now have the Lewis structure for carbon monoxide. So I have a triple bond between them. Okay, that's 6 electrons shared between carbon and oxygen. Carbon has a lone pair, so that's 2 electrons right there. Oxygen has a lone pair, that's 2 electrons right there. 2 plus 6 plus 2, that's a total of 10 electrons. So this is your Lewis structure for carbon monoxide. In fact, any diatomic molecule or ion that has 10 valence electrons is going to have a triple bond and a lone pair on each atom. Okay, so if I were to ask you, what's the Lewis structure for nitrogen? N2. Well, you're going to say each nitrogen has 5 valence electrons. It belongs to group 5A. So now N2 would give me 5 valence electrons times 2. That's 10 valence electrons. It's going to look just like carbon monoxide. A lone pair on each nitrogen and a triple bond between them. Okay, that takes care of 10 valence electrons. And that sort of explains why nitrogen, as it exists in nature, in the air that you breathe, okay, in fact, that's 80% of the air you breathe, it's N2, diatomic, and it's not just a collection of individual nitrogen atoms. By sharing 3 pairs of electrons between them, the 2 nitrogen atoms are able to acquire a noble gas-like configuration around them, and so that's something we associate with stability. All right, here's another example. This one is to illustrate the fact that hydrogen atoms can only form single bonds. So we said they have to be a terminal atom. So if I were to ask you to draw the Lewis structure for H3O+, okay, how are you going to connect the atoms? You have to do all single bonds, right? But you cannot put hydrogen between 2 atoms. So this is not going to work, okay? You have 2 bonds around the hydrogens, and that's not going to work. The only way you can draw this structure is to put the hydrogen around the oxygen. So you have hydrogen here, and hydrogen here. So that's your first step when you do your single bonds. Second step is you complete the octet around each atom, and keep in mind hydrogen only needs a duet, so hydrogen's, as long as hydrogen has a single bond, it's happy. You don't need to do anything with it anymore. So let's look at oxygen. This has 2, 4, 6. Okay, so we need one more pair on the oxygen, so I need that extra pair. I'll show that as a lone pair on the oxygen. Okay, so that was my step 2. And now you count your valence electrons. How many valence electrons do you have? You have 2, 4, 6, 8. Okay, so 8 valence electrons. Should you have 8 valence electrons? Well, oxygen belongs to group 6A, so that's 6 valence electrons. Okay, let me see. 6 valence electrons for oxygen. Each hydrogen, there's 3 of them, so that's 1 from each hydrogen times 3. That's a total of 3. So 6 plus 3 is 9. Okay, but there's a plus 1 charge here, H3O plus. This, by the way, is hydronium ion, if you recall. Okay. There's a plus 1 charge, which means that's 1 less electron, right? So minus 1, that gives you 8 valence electrons. So this structure is correct as far as number of electrons is concerned. It's got 8. So to complete this structure, what I'll need to do, let me rewrite it over here. HOH, and there's another H to oxygen bond there. So you have 3 single bonds, a lone pair on the oxygen, but there's a positive 1 charge for the whole thing. So I put them in square brackets and put a positive 1 charge, a plus on the upper right hand corner. So that would be the Lewis structure for hydronium ion. Okay. Now, like I said, if you were to do Lewis structures for diatomic molecule like N2 and CO, if you have 10 valence electrons, the structure you'll come up with would be one where you have a triple bond between the two atoms, and each atom has a single bond, has a lone pair around next to it. Okay, so this is 10 valence electrons. So carbon monoxide has a triple bond, a lone pair on the carbon, and a lone pair on the oxygen. So if you only have 10 valence electrons for a diatomic species, a molecule or a diatomic ion, then you know that that's the structure you need to draw. Here's the other possibilities for diatomic molecules. If you have a double bond between them, then, so let's say you have 2 atoms with a double bond between them. The way you complete the octet is for A here, since it's already got 2 pairs, it needs 2 more lone pairs. And your X over here, since it already has 2 bonding pairs, it's going to need 2 more lone pairs. So if you have a double bond between 2 atoms in a diatomic molecule or ion, then this is what the structure is going to look like. Okay, so if you count the add electrons here, you have 2, 4, 6, 8, 10, 12. So anytime you have a species that has 12 valence electrons, it's going to look like that. It's going to have 2 pairs of electrons shared between the 2 atoms. If you have 10 valence electrons, it's going to show a triple bond. Okay? If it has 14 valence electrons, as we've seen earlier, you're going to get a single bond between the 2 atoms. Okay? And if you have one atom with only a duet right here, then that A must be a hydrogen, right? So if you have this one, would take care of 8 valence electrons. And of course, if you only have a single bond between the 2 atoms, you're really referring to a hydrogen molecule here, H2. Okay? So there's 5 possible ways of drawing a Lewis structure for a diatomic molecule of our ion that satisfies the duet rule. Okay, so how many valence electrons are shown for each? These 5 ways you can have either 2 valence electrons, 8 valence electrons, 14, 10, or 12. All right, and the atoms above here that are H's are the ones that are shown as A in structure 1 and 2. Okay. So these must be, this A right here must be an H because it only has a duet. All right, so based on that, let's look at this clicker question. Which of these does not have a single bond? H2, HF, F2, O2, or peroxide? That's O2 with a negative 2 charge. Which one does not have a single bond? Let me get you started with H2. H2 would, each hydrogen would need to form a single bond. The only way hydrogen can bond is through a single bond, so it can't be H2. All right. And if you look at F2, fluorine here has 7 valence electrons, column 7. So 7 times 2, that's 14 valence electrons. All right, so I think I'll give you a little time to figure out the rest. Which one does not have a single bond? Okay, D, very good. If you look at oxygen, it belongs to group 6A, 6 times 2, that's 12, so that means it has to look like structure number 4 right here. Okay, so you're going to have a pair of oxygen atoms with a double bond between them, and each oxygen atom has has 2 lone pairs on it. Okay, and again, this sort of explains why oxygen, as it's found in nature, is diatomic. Okay, oxygen in the air you breathe is O2, and by pairing up, oxygen atoms are able to acquire a noble gas-like configuration. HF would have a single bond, 3 lone pairs on the fluorine. That's 8 electrons. 1 plus 7 is 8. And F2 had 7 valence electrons times 2. That's 14. That means you're going to have a single bond between the fluorines and 3 lone pairs on each of the fluorine atom. And peroxide, O2 with a negative 2 charge, that's 6 times 2, that's 12, but there's an extra negative 2, there's an extra 2 electrons because of the negative 2 charge, so that's 14 electrons. So for peroxide, your Lewis structure is going to have a single bond, 3 lone pairs on each oxygen, but that structure as shown is not complete because you still have to draw brackets around it and put a negative 2 charge on the outside. Okay? Okay. Clicker question right here. This should be easy. Let's just skip that one. This one's also easy. Skip that one. Let's try this one. How many valence electrons must be shown in the Lewis structure for carbonate ion? Carbon's right here, oxygen's right here. So carbon's group 4A, oxygen's group 6A. Is it 20, 22, 24, 30, or 32? See? Let's see. Carbon should have 4. Right, group 4. Oxygen's group 6A. So oxygen gives you 6 times 3. That gives you 18. And there's a negative 2 charge. So that's 18 plus 4 plus 2, 24. Very good. Which of the following has a double bond? HCl, O2 with a -2 charge, nitrogen, or PF. So here's hydrogen, there's chlorine, oxygen, nitrogen, and fluorine. Which one has a double bond? And phosphorus is down here. B, C, and D. Okay, let's look at HCl. HCl, obviously hydrogen can only have a single bond, right? So that can't be right. In fact, this is what HCl is going to look like. Chlorine has 7. 1 plus 7, that gives you 8 valence electrons. Okay. Peroxide, we already talked about that. That's 14 valence electrons. 6 times 2 is 12, and then a -2 would give you 2 more, and that's 14. That's going to be a single bond. So peroxide is going to look like this, single bond. Nitrogen, we've already talked about this one. You have triple bond between the two nitrogens. 2 nitrogens will give you 10 valence electrons, so N2 is going to look like this one. So the only remaining choice is PF, and let's look at PF. Phosphorus has 5, okay, and the oxygen and the fluorine has 7. 5 plus 7 has 12 valence electrons, so PF is going to look like this one. You have a double bond between the fluorine and the phosphorus, and 2 lone pairs on each of those 2 atoms. Okay, so the correct answer is D. All right. Consider the following partially drawn structure of 2-butene. So you have carbon, another carbon, a double bond between the carbons, and a single bond between another carbon, another pair of carbons. When you complete this structure, okay, the formula is C4H8. So I'm missing some hydrogens here. Where am I going to put those hydrogens? When this structure is completed, how many hydrogens atom would be bonded to the first carbon? Well, let's work this out. Let me draw this again down here. Carbon, carbon, double bond, carbon, single bond, carbon. All right, first thing I need to do is attach my hydrogens, okay? And so, well, first of all, I need to put pairs around the carbon to give each one an octet. So if I were to give this first carbon an octet, I need 3 pairs around it, okay? This middle carbon right here has already 1, 2, 3 pairs around it, so it's going to need a 4th pair to give it an octet. So I'll put a lone pair there for now. This carbon right here already has 1, 2, 3 pairs around it, so it just needs 1 more pair. So I'll put another pair there. And this last carbon right here, okay, has already 1 pair, so I need to put 3 more pairs on it. Okay. Now I have to attach 8 hydrogens, so I can put the hydrogen on any of those pairs. Okay, so I can put 1 hydrogen here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So that means this structure is going to look like, I can clean this up a little bit. So you have CH bonds, 3 CH bonds here, carbon-carbon double bond. This carbon has to have a bond to a hydrogen, and this carbon has to have a bond to another hydrogen, and this carbon would have to bond with 3 other hydrogens. So this is the structure of 2-butene, okay? That's the name of this compound. And so how many hydrogen atoms would be bonded to the first carbon? The answer to this question would be 1, 2, 3. Okay? All right, let's talk about isomers now. There may be more than one way to connect the atoms in a Lewis structure. Anytime you have more than two atoms in a molecule, there's going to be more than one way of connecting them. Each of these unique ways of connecting the atoms would represent a different molecule, a different compound, but since they have the same number of atoms of each kind, okay, we call them isomers, okay? But each isomer will be represent a different molecular ion. For example, hydrogen cyanide and hydrogen isocyanide. If your atoms are connected this way, HCN, you'll notice carbon is sandwiched between the hydrogen and the nitrogen. It will be different as compared to a molecule where the nitrogen is sandwiched between the carbon and the hydrogen. Okay? So these two would be called isomers, but let me complete this Lewis structure first. Hydrogen, if you recall, contributes 1 valence electron. Nitrogen gives you 5, and carbon gives you 4, right? So that's a total of 10 valence electrons, 1 plus 5 plus 4. So if I were to complete this structure, this is what I'll see. This is what I'll come up with. Okay, 10 valence electrons. You have a single bond here, triple bond here, a lone pair. So that's 2 plus 6 plus 2. That's 10 valence electrons. Same thing here. This is 2. Okay, plus 6 plus 2. Okay, that's 10 valence electrons. So these two represent different molecules. They represent different compounds. Okay, so HCN is what you call hydrogen cyanide. This is hydrogen cyanide. And HNC is hydrogen isocyanide. So there's two ways of drawing a Lewis structure for a molecule that has a hydrogen, a carbon, and a nitrogen. And both of those happen to exist, okay? So you call them isomers. Now, for a given way of connecting the atoms, okay, so we say, remember we said there may be more than way of connecting the atoms. We say there may be more than one connectivity, okay? For every possible isomer, okay, then even for a given isomer, for a particular way of connecting the atoms, there may be more than one way of distributing the valence electrons. So even if the atoms are connected the same way. So each of these unique ways is called a resonance structure. So for example, OCS, I can draw that. Okay, OCS, I can connect it the same way, but I can distribute the atoms differently. Okay, so for example, OCS, I can draw it like this. Carbon triple bond over here with the oxygen and a lone pair, a single bond with the sulfur, and 3 lone pairs here. Okay. Or I can put the triple bond between the carbon and the sulfur and a single bond between the carbon and the oxygen, and I'll have the lone pairs on the oxygen. That's one way of doing it. And I'll have a lone pair on the sulfur. Or another way I could draw it is I can draw a double bond between carbon and sulfur, a double bond between carbon and oxygen, and I'll just have 2 lone pairs on this oxygen and 2 lone pairs on this sulfur. Let's verify that we have the same number of electrons on all of these, okay? So you have 2 plus 6, that's a triple bond, plus 2 plus 3 lone pairs, that's 6, right? Or another way of looking at it, a quicker way to add things is as follows. You can do something like this. You can say, all right, that's 8. That's an octet around the oxygen. That's an octet around the sulfur. So 8 plus 8, that's 16 valence electrons. This one also has 16. That's 8 around the oxygen. That's an octet around the oxygen. And you also have an octet around the sulfur. So that's 16 valence electrons. Here you have 8. You have 2, 4, 6, 8. All right. Let me rewrite this. So you have 8 there, and you also have 8 here. So that's also 16 valence electrons. So all of these represent a Lewis structure that has 16 valence electrons. Should we have 16 though? Oxygen contributes 6, carbon contributes 4, and sulfur contributes 6 valence electrons. Oxygen and sulfur are in the same column in your periodic table, so that should show you 16 valence electrons. So look at these 3 structures. They all have an octet around carbon, oxygen, and sulfur. They all have 16 valence electrons. So those are different way, and it's connected the same way, carbon between oxygen and sulfur. Okay, note that if I drew it like this, SCO is the same thing. Okay, carbon is still between oxygen and sulfur. All right, so SCO and OCS would be the same thing. Now, what would be different would be if I had like COS. Now you have your oxygen between carbon and sulfur. That would be a different isomer if there was such another connection, if that was possible. Okay. So anyway, these three possible distributions of electrons for the same connectivity of atoms are what we would call resonance structures. Okay. Now, anytime you're able to draw more than one resonance structures that seem equally feasible, what would that suggest is that the reality is a hybrid of these resonance structures. In other words, that would suggest is maybe none of those structures is an accurate representation of reality. The real distribution of electrons in the atom, in the molecule, would resemble more like a hybrid of those. Okay, so that's what a resonance structure means. Okay, so how do we know? One thing you do need to realize is some resonance structures, as I mentioned earlier, are more feasible are more plausible than others. Okay, so they're more reasonable than others. So how do we know whether a resonance structure is going to be more significant than another? Or how do we know what is the more likely isomer you're going to find in nature? Okay, and some isomers that you can draw on paper you may not find in nature. Okay, when you draw multiple resonance structures, some of those resonance structures may resemble reality more than the others. And the way you figure those out, which one is more significant, is to look at what we call formal charges. Okay, and the way you figure out formal charges is as follows. First of all, formal charges that are small, 0, +1, -1, are better than structures that have formal charges that are larger. So if you see a formal charge of +2, that's not a good sign. If you see a formal charge of -2, that's bad. Okay? So when you draw lower structures, you want to draw structures that have small formal charges. And you don't want neighboring atoms to have this formal charge of the same sign. So for example, if I have two neighboring carbon atoms and I figure out the formal charges for both of those would be positive, that's not good. Chances are that structure you just drew is very unlikely, okay, to correspond to reality. And anytime you have neighboring atoms, the more likely structure is also, as far as resonance is concerned, if you have a more electronegative atom, they tend to have the negative formal charge. When you have two atoms sharing electrons, an atom that's more electronegative is the one that pulls electron more strongly. Okay, so let's look at how we can calculate formal charges. The formula is this: a formal charge is the number of electrons, valence electrons, that a free atom would have. A free atom is an atom, it's just a neutral atom. That's the atom we talked about at the beginning of the semester. It's just, for example, an oxygen atom, the number of valence electrons that it have would be 6. Okay, so it tells the number of electrons that atom would contribute to the structure. A is the apparent number of electrons that the atom appears to own in the structure. So what it appears to own in the structure is A right here. Let's illustrate that with this example right here, sulfur. In this structure of SCO, if you look at sulfur, okay, on your periodic table, it's in group 6. So F for sulfur is 6. It will contribute 6 to the structure. Okay, a free sulfur atom would have 6 valence electrons. It appears to own, how much does it appear to own in this structure? Well, the rule is lone pairs belong completely to the atom. Shared pairs are shared 50-50. Okay, so the lone pair is 2, right? That's 2 electrons belonging to sulfur because of the lone pair. Half of the 3 bonding pairs, what's half of 3 pairs? 3 singles, right? 3 pairs is 6 electrons, so 6 divided by 2 is 3. So in this structure, your sulfur appears to own 5 valence electrons. So 6 minus 5 is negative, let's see, It's positive 1, okay? So what we're saying is the sulfur here is a formal charge of positive 1. That means that it appears to have lost 1 electron. Remember, a positive charge implies a loss of electrons. It hasn't really lost 1 electron, but the way we've drawn it, it appears to have lost 1 electron. So you call that a formal charge of plus 1. Let's try the formal charge for carbon right here. Carbon by itself is going to contribute. It belongs to group 4A. Okay. A free carbon atom would have 4 valence electrons. Okay. It appears to own how much? It has 1, 2, 3, 4 bonding pairs. Half of the 4 pairs would be 4 singles, so it appears to own 4. So 4 minus 4 would be 0. So the formal charge of carbon here is 0. The formal charge of sulfur is plus 1. And one thing you'll realize when you do a lot of these is that formal charges will just add up to the charge of the whole thing. Since this is a neutral molecule, you would expect the formal charge of oxygen here to be negative 1. Okay? Let's try that for oxygen. You'll see in the case of oxygen, a free oxygen atom will own 6 valence electrons, group 6A. It appears to own, in this structure, how many does it appear to own? 6 in the lone pairs, 2, 4, 6, okay? Plus, half of the pair would be a single, so plus 1 more electron, half of that pair. So it appears to own 7 electrons in this structure, so F minus A, 6 minus 7 is negative 1. In this structure, we say oxygen appears to have gained 1 electron. So our formal charges are plus 1, 0, negative 1. So that's not too bad. Okay? Now, if you were doing SCO like this, if you had double bonds instead, okay, you'll find that if you calculate the formal charges for this, you'll end up with 0, 0, and 0. So this would be a better resonance structure than this one's. Okay? Oh, by the way, I forgot to mention, if it's possible to draw more than one resonance structure, when you draw them, you can, what you need to do is put them side by side. Okay, so this one right here, I can do O, C, S, okay? And then I draw a double-headed arrow between the structures. And then I can do O, C, triple bond S. And then another double-headed arrow with a double bond on both sides. Okay, oops. So I put them in brackets right there. That would be a way to represent resonance structures. Okay, so like I said, when you draw resonance structures, what you're saying is reality is neither one of those, not a single one of those. It's probably a hybrid of those. Okay, so the distribution of the electrons. It's like saying a mule sort of looks like a horse, sort of looks like a donkey, but it's not a horse, it's not a donkey, it's a mule, it's a hybrid. Okay, where am I? I think I just lost my place. All right. Now, when you're dealing with a lot of molecules, you want to go for 0 formal charges when you try to draw molecules. Okay. It's not always going to be 0, but if your best bet would be to draw a structure that has 0 formal charge, and you can do that when your hydrogen has 1 single bond. Okay, and that's why, in fact, hydrogen, that's the only thing hydrogen does, forms a single bond. Because if it forms a single bond, a free oxygen has 1 valence electron. If it forms a single bond, what's half of a pair? 1 single, right? So it will appear to own 1. It will have a formal charge of 0. Now, if you have carbon, okay, you have 4 bonding pairs, okay? So that would give you a 0 formal charge when carbon has 4 bonding pairs. Why is that? Because carbon would by itself would have 4 valence electrons. If it has 4 pairs, half of 4 pairs would be 4 singles. 4 minus 4 would be 0. So if you, anytime you see carbon with 4 bonding pairs around it, it will have a formal charge of 0. In fact, in a lot of molecules that have carbon in them, majority, super majority of those molecules will have carbon. It's pretty much all of them actually will have carbon with 4 bonding pairs. So this is one way carbon can bond. Another way would be 4 pairs. So you can have a double and 2 singles. That's 4 bonding pairs. That will also have a formal charge of 0. Okay? Or you can have a triple bond and a single. Okay? That's 4 bonding pairs around carbon. Or you can have carbon with triple bond, with a double bond on both sides. So you can see carbon is very flexible. It's very versatile in the way it can link up with other atoms. It can link up with other carbon atoms, so you can form large molecules of chains of carbon atoms, as we've shown you earlier. So like you can put in a chain 4 carbon atoms, and you get what's called butene. Okay, and so because of this versatility, you have pretty much an entire sub-branch of chemistry, a sub-discipline of chemistry called organic chemistry, just deals with the kinds of molecules that carbon can make. So these types of compounds are called organic compounds, organic molecules. Okay. Now nitrogen, you can have a formal charge of 0 if your nitrogen has 3 bonding pairs and 1 lone pair. Because if nitrogen forms 3 bonding pairs and a lone pair, what do you get? By itself, nitrogen will contribute 5 valence electron to the structure, right? By itself, nitrogen has 5 valence electrons. If it looks like this, it has 3 bonding pairs, it will appear to own. Okay, you got the lone pair right here, that's 2. Okay, plus half of the 3 bonding pairs would be 3 singles, so 2 plus 3, yes, okay. 2 plus 3 would be 5, that's a total of, that's 5 minus 5, that would be 0. Okay, so nitrogen will give you 0 formal charge if it has 3 bonding pairs. So it can do 3 single bonds in a lone pair, as shown here, or you can do a single bond in a lone pair, a single bond, a double bond in a lone pair. Okay, or it can have a triple bond, like in nitrogen, in the diatomic nitrogen molecule. Okay, triple bond and a lone pair. So for example, in N2, each of these nitrogens have a triple bond and a lone pair. The formal charge there is 0. Okay, I think this would be a good time to stop.